Hello everyone, welcome to lecture 3 of week 9 of the course Power Network Analysis. In this lecture, we will start with our second last module, which is fault analysis, and specifically we will understand why this analysis is necessary, not only in this lecture but also in the next lecture. And the discussion that we are going to have is how what is the impact of a fault. So what exactly is a fault, first of all, and what is the specificity behind the behavior of a typical conventional synchronous generator during a fault. Regarding that, we would understand more in today's discussion. So this lecture is going to be more about the variation in the synchronous machine parameters, specifically the synchronous reactance of the synchronous generator, which we have indicated by X, and the associated time constants that come in. We'll spend more about the discussion on time constants, preferably in the next lecture. In today's discussion, we will talk more about this, that if a fault occurs, so first of all, what is a fault? We'll understand that. And if a fault occurs, then how does this synchronous machine, which is the major source of electrical power, how does that machine particularly behave during a fault? So till the previous lecture, we had finished with different techniques involved in the steady state analysis of a given AC network, both for transmission as well as distribution systems. And we talked about different techniques starting from Gauss-Seidel method till next being Newton-Raphson method. Then we had fast decoupled method. Then we also had the DC model. And finally, we also talked about the backward forward technique for distribution network, which is a very specific technique for ease in solving power flow equations for distribution network. The first four methods being primarily used for the high voltage transmission network. Before I go further, I have probably not explained clearly something about the DC model. So if you recollect the DC power flow lecture discussion, therein our voltage phase angles, bus voltage phase angles theta, they were expressed in terms of a X matrix, which was again getting multiplied with the power injections at all buses except the slack bus. So this vector equation was not applicable for the slack bus, because for the slack bus the phase angle reference is already known or defined. And this X matrix that we discussed, this X matrix was actually inverse of the B dash matrix, where B dash is the matrix which was also used in the first half of fast decoupled power flow method. So this X matrix, it's actually the inverse of B dash matrix, which is part of Y bus obtained or used in the first half of fast decoupled power flow. This X matrix should not be confused with the matrix which is based on the actual line reactances. So let's say if we have a bus, if we have two buses which are connected by a transmission line of reactance XMN, the buses being M and N, the line reactance is XMN. This XMN appears as part of B dash matrix, and it has directly nothing to do with the capital X matrix which was used in DC power flow. That was one point. The second point was, after obtaining all these phase angles, we also saw that the power flow from bus M to N on line connecting them is nothing but theta M minus theta N divided by small xmn, where xmn is the actual line reactance. This xmn should not be confused as m comma nth element of X matrix. This inference should not be done. This is absolutely incorrect. XMN here actually is the actual line reactance. So just wanted to emphasize these 2 points before we go further. So coming to our module of interest, which is fault analysis. How do we define a fault? A fault is any disturbance in the power network which interrupts the flow of normal current. This normal current is flowing from the sources to the load. So we would also refer to this current, normal current, as the load current also. So any such event or perturbation or disturbance which hampers a particular load getting its corresponding current from the source would be called as a fault. And why does this fault occur? Power network is a man-made network which consists of several elements, components, starting from source, transformers, transmission lines, distribution lines, both underground and overhead, and then you have step-down transformers, substations, circuit breakers, etc. So there are a lot of components involved behind setting up this power network. So any such element or component, when it fails due to manual intervention, probably due to maintenance or due to aging effect or being continuously operated, so every element or every component would have its own lifespan. So any of those activities, either prolong use of a particular element or maintenance scheduling perspective, if the system element is no more operational, it might interrupt the normal flow of load current, and that is what we would call as a particular fault. So in general, the category or basket of faults is going to be large. In fact, there's another inference behind defining a fault. The other inference is that typically when a fault occurs in a power network, the bus voltages, they tend to go down. That is a typical signature behind any particular fault. The bus voltages tend to go down from their actual values, whereas the current, the current in the line or the current injection at a particular bus, that tends to go up. This is a very typical signature behind any of any fault that occurs in a power network. Any activity or event which does not follow this particular signature, we would not classify it as a fault. And why this signature happens, please have patience. We will come to this particular signature of voltage going down and current going up as we go deep into the individual faults that we would consider. So at the outset, having said that a fault is any disturbance that interrupts the flow of normal load current, the fault can again be categorized into two classes, one being the symmetric faults, the other being a asymmetric fault. Since our power network is a three-phase network, so if we have a transmission line where the three lines correspond to phase A, phase B, and phase C, and if a fault has occurred which is equally affecting all the three lines, then it is imperative that the normal flow of current which was through these transmission lines to some far off load, this load would not get the usual flow of current, and all the three currents would be equally affected. So symmetric faults are those cases where all the three phases, from the perspective of current or voltage, they have similar pattern or diminishing behavior or increased behavior. Asymmetric faults are those cases where three phases of the line, they exist, but instead of equally affecting all the three phases, either only one phase gets affected or together two phases get affected. The third phase, at least from one of the three phases, is not getting equally affected, and that would be called as unsymmetric faults. So there can be different, again, categories of unsymmetric faults. As I mentioned, if two phases are getting affected, we would call them as phase-to-phase fault. If one phase is getting affected, then we would call it as a phase-to-ground fault, and there can be several other combinations of unsymmetric faults. So we will not go deep into that category yet. We'll take it up probably in the third or the fourth lecture of this particular fault analysis module. What we would more be interested is that, having understood that a fault would have this particular signature, let's understand that, okay, what is the impact of this particular signature where during a fault the current tends to go up. So let's see that. So in our previous discussions, previous modules, like the power flow analysis module, where we have discussed about the steady state behavior of power network at length. During the synchronous generator module also, we have discussed about the synchronous generator steady state model at length. And during that discussion, we understood that for a cylindrical rotor machine, the machine equivalent model or equivalent circuit representation will have a constant EMF, electromagnetic force, or internal EMF behind a synchronous reactance XS. And this synchronous reactance is a component of the armature MMF reactance, which is the linkage with the stator flux, as well as the air gap flux, as well as the rotor MMF flux. So synchronous reactance comes because of all those aspects considered together: the leakage component, the linking between stator flux and rotor flux, and so on. For a non-cylindrical pole machine or for a salient pole machine, we also understood that since the air gap is not uniform in a salient pole rotor, the air gap is minimum along the direct axis and maximum along the quadrature axis. So a salient pole machine, instead of having one unique synchronous reactance, tends to have two unique reactances, which we call as XD and XQ, XD being higher than XQ. Usually, in fact, in practical cases, XD is much larger than XQ, because the air gap along the direct axis is minimum, so more linkage happens along the direct axis. The air gap being maximum along the quadrature axis, the corresponding linkage is also minimum. All these discussions which we had discussed about the steady state operation, the same won't be true in the event of a fault. Or for that matter, during a disturbance which is happening just at the terminal of a synchronous generator. If we understand why this steady state behavior is no more applicable for a disturbance or a fault, for a synchronous generator case, we can also extend this discussion for a fault or disturbance happening elsewhere in the power network also. So we'll focus more on the synchronous generator behavior specifically, and then we'll extend this as and when required for faults along at any point in the other point in the power network. So usually in this statement, I have just emphatically mentioned to mean about the event of short circuit or fault. So basically, short circuit is also a type of fault in which the flow of normal flow of load current is interrupted. The short circuit refers that the current is getting another path of least resistance. Currents tend to always flow in the path of least impedance or resistance. So during a short circuit event, the current is trying to flow through another path which is having least impedance or resistance and not flowing through the usual transmission lines, so that the loads can get their corresponding power. So by short circuit, I specifically mean that during a fault or even during steady state conditions, what we have seen that typically for a well designed synchronous generator where the resistance or winding resistance can be neglected, the overall stator current, it tends to be lagging the corresponding internal EMF or the terminal voltage in that manner also by almost 90 degrees, because the overall synchronous generator circuit, if the resistance is neglected, becomes purely reactive or inductive circuit. And for a pure inductor, the currents tend to lag the corresponding applied voltage by 90 degrees. So it is not just during the fault, but in usual operation during steady state also, the stator current of the synchronous generator tends to lag the corresponding applied or terminal voltage by 90 degrees. And for salient pole machines, since the direct axis reactance is larger, and as I mentioned here, the value is much larger than the quadrature axis reactance. So in terms of armature reaction, the armature reaction MMF, which is produced due to stator excitation, it would mostly lie along the direct axis. Least part of it would lie along the quadrature axis because of the large distance. Not much of armature reaction would link to the corresponding rotor windings or rotor current. It would mostly get impacted along the direct axis because the direct axis gap is minimum. So any armature reaction effect which comes in because of rotor current, it is linked to the rotor along the direct axis, and that's the reason why I have mentioned that it is centered almost on the direct axis during typical steady state or transient operation. The catch behind all this discussion is that right after a disturbance or a fault at the terminal of a synchronous generator or a machine, the machine reactance, which we call as XS for cylindrical pole machine, or if we talk about the dominant reactance for a salient pole machine, the value of X, either XS or XD, it doesn't remain constant. It varies with time as the machine experiences a fault or a disturbance. And we'll understand why this variation happens. Please have patience. We'll get into that aspect, but I'm just trying to emphatically state the reason of the discussion that we are going to have. So because this machine reactance is varying, the generator's response, or for that matter, the power network's response after a fault can be categorized into three distinct periods. The first one which appears is the subtransient period, which is just after a fault or a disturbance at the terminal of a synchronous generator, followed by a transient period which is little bit larger compared to subtransient period. Subtransient period typically lasts for 1 to 5 cycles, whereas transient period would be there for few hundreds of cycles, followed by the last steady state period in which the RMS values of voltage and current don't tend to change. During subtransient and transient period, the currents and voltages have time variations because the machine reactance is also varying with time. And overall, during the steady state analysis, which we have discussed earlier, we have emphatically discussed about the steady state period only. We have not prior discussed about subtransient and transient period. Now, why would these periods exist? It again goes back to this philosophy that the machine reactance is not constant. So, in terms of the current envelope, this is basically the short circuit current. Basically, it is the stator current which is being plotted typically for a synchronous generator which has experienced a fault at time t is equal to 0. And this is a typical signature, a current signature that appears, that the current would tend to go up compared to its previous steady state value, which is noted by this steady state, which is not noted by this dotted line. The current magnitude would tend to go up and it would have its maximum peak during the subtransient period, or we call it as subtransient envelope, and gradually this peak current tends to decay in the transient envelope. The decay is still not 0. So, and finally, after the decay has happened at t is equal to infinity, the steady state period would come in, which typically happens after a few hundreds of cycles. So, depending on the machine parameter, which is essentially the value of inductance L, which the machine is exhibiting, and the associated resistance value R, the subtransient, transient and steady state periods, the steady state period doesn't get affected much, but the subtransient and transient period, they would have strong dependency on how inductive the machine is and how lossy or lossless the corresponding synchronous machine is. So, we'll again understand why this current behavior happens just after a fault at t is equal to 0 on the terminal of the synchronous generator. Please have patience and please bear with me. Before I explain why this variation happens, first of all, let us understand the premise of how this variation is happening. So, there is a theorem known as constant flux linkage theorem, which can be useful in understanding this behavior in machines reactance. So, what I have not explained till slide 6 was why this current becomes peaky and then tends to decay. Assuming that the synchronous machine stator current per phase armature current has this behavior, assuming that, we can apply this constant flux linkage theorem and then understand in a reverse engineering fashion that why the synchronous machine parameter has variations at all. So, what it states is that in an inductive circuit, the flux linkage along any closed circuit with finite resistance and reactance, it cannot change instantaneously if there is a EMF source present. If there is no active source in the corresponding closed circuit, there is no question of flux linkage appearing in at all. But if the circuit has a EMF, the flux linkage in a closed circuit of finite resistance and reactance cannot change instantaneously. The reason being, the corresponding reactance or the inductive effect will always obviously have a finite permeability. permeability, and permeability sort of resists the change in corresponding magnetic flux linkage, which also appears in because of the variation in the corresponding synchronous machine parameter. And for our discussion to sort of apply this for salient pole machines, we'll assume that XD is the dominant reactance. So we'll correspondingly ignore the value of XQ and look at it from the perspective of how XD has its variation. For salient pole machine, it is all about XD, whereas for cylindrical pole machine, it is all about the synchronous reactance XS. So in case of three-phase fault at the generator's terminal, by three-phase fault I mean all the three phases of the generator terminal, they are equally getting shorted through some fault, and the corresponding synchronous generator current is not able to flow to the corresponding load. Rather, this current is bypassing through this particular terminal to the ground or any other short circuit path. And since I have given the assumption that the armature current increases significantly, so assuming that the armature current tends to follow this particular envelope on slide 6, we'll try to understand why the machine reactance tends to have this variation by understanding the constant flux linkage theorem. So as per constant flux linkage theorem, numerically we can associate or state that the flux linkage psi is function of L and I. And if during subtransient period the value of I is at its maximum, it is imperative that by constant flux linkage theorem, where flux linkage cannot change instantaneously, the associated L, if the current is at its maximum, the associated L would be at its minimum during the subtransient period. Then during the transient period, as the current tends to go down, the corresponding L value would tend to go up, and finally in steady state, the current is at its minimum and corresponding L would then again appear at its maximum, so that the product of ILL during transient, subtransient and steady state period, this factor doesn't change much, doesn't change instantaneously. Physically, what happens, what leads to this lowest value of L or reactance in subtransient period is that during subtransient period, just after a fault when it has occurred, the stator flux lines, being highly inductive circuit, the stator flux lines, they do not link to the field winding or rotor winding at all. Rather, they are locally concentrated. They only just pass out of the stator core, pass through the air gap and link more with the damper windings rather than linking much with the rotor winding, because damper windings, they are short circuit windings, so they don't have initial current, so they don't offer much of impedance or resistance to this change in constant flux linkage. During subtransient period, the linking between stator and rotor winding starts increasing, so more of stator flux, it starts linking with the field windings and the remaining damper windings, which leads to more demagnetization and more reactance, and hence the corresponding reactance tends to go down, tends to go up as compared to the subtransient period, but still it is not that high as compared to the steady state period because of the demagnetization which has started happening. So the value of L here is at its minimum because there is not much linkage to the rotor winding. Most of the air gap, most of the flux is linking only to the air gap and some of the damper windings. In the transient period, the linkage effects has gone up, so the value of L tends to go up because L basically is a linking effect between rotor and stator. And finally, in steady state, almost all the flux links to the rotor winding and field winding, and the corresponding value tends to go at its maximum high possible value. So that is the overall essence or basic reason behind why synchronous machine reactance does have variation. We still have not understood or thought about or discussed about why the current would have this particular behavior as shown in slide 6. So we'll take up that probably in the next lecture. Just to sort of conclude or in a way to summarize, with neglect of armature resistance for a well-defined machine, the machine impedance is mostly reactive or inductive in nature. This is true under normal and short circuit condition, and that's the reason why armature current, stator current would almost always lag the internal EMF or terminal voltage by almost 90 degrees. IQ is not so significant, so we are considering most of the impact for XD, which is the direct axis reactance for salient pole machine, hence XD is of importance. So in general, if we have to represent or state that the XD dash, which is the subtransient reactance, XD single dash is the transient reactance and xd is the steady state reactance. The corresponding values of reactances, because of constant flux linkage theorem and assuming that the current tends to go up in subtransient, goes down in transient, and finally reaches a steady state value. This is the typical signature or behavior or performance of a synchronous machine in terms of its reactances. We'll take up this simple example to sort of understand what is the application or implication of these different reactances. So what we have here, we have a 3-phase 60 Hz synchronous generator or machine which is running at constant synchronous speed. The armature windings are initially open circuited, so there is no question of armature reaction appearing at all. And the field voltage is so adjusted that the terminal voltage at the synchronous generator is equal to 1 per unit. The voltage actual rating is not given, but the machine reactances under different subtransient period, transient period and steady state period are given. In case a short circuit fault occurs at the terminal of the machine, we have to find the corresponding steady state, transient and subtransient short circuit currents. So since the machine is open circuited, the armature current does not exist before the fault. The fault event is the only singular event which is happening in this synchronous machine. So the corresponding value of xd double dash, xd dash and xd, if you see, they tend to follow this particular inequality relationship as per the discussion that we had. And if we have to find the corresponding steady state current, then it is imperative that to find the steady state current again in per unit, which sort of reactance should we consider? Should we consider the subtransient reactance to find steady state current? Should we consider the transient reactance to find the steady state current, or should we take the steady state value of x to find the steady state current? So essentially that is what is shown in this particular expression here. ID is dependent on the steady state reactance, assuming E naught, which is the internal EMF, which is again given as 1 per unit. So 1 by 1.2 is the steady state current, and if we try to find this current in transient period, xd dash value is lower than xd, so the corresponding transient current would be higher, and the maximum achievable peak in subtransient period would be the maximum possible value depending on the xd double dash. Since the reactances follow decreasing order from steady state to the subtransient period, the currents also tend to follow increasing behavior from steady state to the subtransient period, indicating that the machine transient reactances are not the same. We'll take up the next discussion or lecture on understanding what these time constants are and what is the behavior of a synchronous machine, specifically in terms of armature current during a fault, just after a fault, and in the steady state. And we'll also understand the difference between fault analysis module and the stability analysis module. Thank you.